Hello everyone and welcome back to our channel. This is part 3 training session for 7QC tool. Hope you have completed last 2 training video of 7QC tool. So let's start today's topic. Generally one question arises in everyone's mind: why do we need quality tools? Generally, we all face challenges to select which tools should be used for problem solving. Then expert do different analysis and got a conclusion that 7 most commonly used tools by which any quality related problem can resolve. There are many ways to solve a problem, such as flow chart, matrix diagram, storyboard, box plot, check sheet, control chart, graphs, histograms, performance index, process capability, survey, cost of quality analysis, critical to quality analysis, deployment flow chart, relation diagram, fishbone diagram, Pareto chart, stratification chart, scatter diagram, tree diagram, YY diagram. Next is, what are the 7QC tools? The 7QC tools provide common method of analysis to help problem-solving teams. It helps in taking decisions faster and objectively as factual approach to decision-making. So 7QC tools are control chart, check sheet, stratification, Pareto chart, cause and effect diagram, scatter plot, histogram. Next is, why we will select control chart for any problem. To find, is there any change in location of process average? Is there any change in the spread of the process? Is there any change in shape? These 3 aspects, location of the process average, spread of the process, and shape of the distribution, are fundamental elements of statistical process control. By monitoring and analyzing data with respect to these aspects, organizations can identify and respond to changes in their processes, ultimately leading to better quality control and improved business outcomes. Next is, what is control chart? The control chart is the fundamental tool of statistical process control, as it indicates the range of variability that is built into a system, known as common cause variation. It helps determine whether or not a process is operating consistently or if a special cause has occurred to change the process mean or variance. Control charts are a critical tool in SPC because they provide a visual representation of a process's performance and help distinguish between common cause and special cause variation. By monitoring and analyzing data using control charts, organizations can proactively identify and address issues that disrupt the stability and quality of their processes. This, in turn, leads to more consistent and reliable outcomes, which is essential for meeting customer requirements and achieving operational excellence. Next is, what is normal curve? The normal curve, also known as the Gaussian distribution or the bell curve, is a fundamental probability distribution with several key characteristics. First characteristics is symmetry. The normal curve is perfectly symmetrical. If you were to draw a vertical line through the center of the curve, the mean, the 2 halves on either side would be mirror images of each other. This means that the data is equally distributed around the mean. Second characteristics is bell-shaped. The normal curve has a distinctive bell-like shape. The peak of the curve occurs at the mean, and as you move away from the mean in either direction, the frequency of data points decreases gradually. This gradual decrease in frequency gives the curve its bell shape. Third characteristics is central tendency. The mean, represented by the peak of the curve, is the central value of the distribution. In a normal curve, the mean is also the median and mode. This means that the most common value in the dataset is the mean. Fourth characteristics is standard deviation. The standard deviation controls the spread or variability of the data. A larger standard deviation results in a wider and flatter curve, indicating greater variability in the data, while a smaller standard deviation results in a narrower and taller curve, indicating less variability. Fifth characteristics is empirical rule. The normal curve follows the empirical rule, also known as the 68-95-99.7 rule. This rule states that approximately 68% of the data falls within one standard deviation of the mean. Approximately 95% of the data falls within two standard deviations of the mean. Approximately 99.7% of the data falls within three standard deviations of the mean. The normal curve is a fundamental concept in statistics and is used in a wide range of applications, from quality control and hypothesis testing to modeling real-world phenomena. It provides a useful framework for understanding. Next is types of statistical data. In statics, two types of data. One is variable data or continuous data, and another one is discrete data or attribute data. Variable data or continuous data, a data which uses the measurement scale as well as inches or time. It contains more information than the discrete data. For example, height, diameter, weight of any product, temperature. Variable data is typically associated with continuous or ratio scales of measurement, allowing for more precise and detailed information. Variable data is quantitative in nature and can be expressed as numerical values, such as measurements in inches, temperatures in degrees, or weights in pounds. It reflects the level of precision and variability within a dataset, making it suitable for statistical analysis to assess central tendency, such as mean or median, and dispersion, such as range or standard deviation. Next is what is discrete data or attribute data. A data which is based on information such as pass-fail. Can't be more specific. For example, numbers of dents on door, numbers of good washers in a lot, numbers of defects in a car, etc. Discrete data consists of values that can be counted, such as the number of cars in a parking lot, the number of students in a classroom, or the number of defects in a manufacturing process. Discrete data often represents categories or labels. Examples include eye color, types of fruits, or product codes. Discrete data is not expressed in a continuous numeric scale but rather as distinct labels or whole numbers. For example, the number of people in a household can be 1, 2, 3, etc., but not 1.5 or 2.5. Unlike continuous data, you typically cannot perform meaningful arithmetic operations like addition or subtraction on discrete data. For example, it doesn't make sense to add red and blue together. Examples of discrete data include the number of students in a class, 1, 2, 3. The number of defective items in a production batch, 0, 1, 2. The number of pets in a household, 0, 1, 2. Types of car models, such as sedan, SUV, truck. Gender, such as male, female, other. Next is what is variation. Dr. Walter A. Shewhart observed, No two items are alike. Variation. Variation occurs in all things. Either predictable patterns or no patterns at all. The study of this variation and its reduction is the principal vehicle of quality improvement. Dr. Schuhart concluded two important principles. 1. Is variation is inevitable, and 2. Is single observation form little or no basis for objective decision making. In this example, there are 8 cold drink bottles. If see 6th bottle, level of cold drink is low. If you see same 8 bottles, you will find one variation is significant, but if you closely see another minor level variation you will find. But this variation is insignificant. Why variation occurs? This is because of equipment's tool wear, machine vibrations, electrical fluctuation, hydraulic fluctuations, fixture positioning. Variation may be due to material's tensile strength, ductility, porosity, moisture contents, thickness. Variation may be due to environment's temperature, light, humidity, pressure. Variation may be due to way of working means method, physical, emotional, skill level of operators. Next is cause of variation. Two causes of variation. One is chance causes of variation and another one is assignable causes of variation. Chance causes and assignable causes are terms often used in the context of statistical process control and quality management to categorize the sources of variation in a process. Understanding these two categories of causes is essential for identifying and addressing issues in a process to improve its quality and consistency. Chance causes, also known as common cause variation or random variation. These are inherent to any process or system and are considered natural, typical sources of variation. Chance causes are often the result of many small, unidentifiable factors that influence the process. The variation due to chance causes follows a predictable pattern and can often be represented by a statistical distribution, such as a normal distribution, bell-shaped curve. When a process is influenced primarily by chance causes, it is said to be in a state of statistical control, meaning it is stable and predictable. Second is assignable causes, also known as special cause variation or non-random variation. These are specific and identifiable factors or events that disrupt the normal operation of a process. Assignable causes are not part of the expected variation and are typically the result of unusual or abnormal circumstances, errors, or external factors. The variation due to assignable causes is unpredictable and may not follow a specific pattern. When a process is influenced by assignable causes, it is said to be out of statistical control, indicating that it is experiencing unusual and unpredictable variations. The key difference between these two types of causes is that chance causes are part of the natural variation that occurs in a process over time, while assignable causes are deviations from the normal, expected behavior of the process. Identifying and addressing assignable causes is a fundamental step in quality management and process improvement because they represent opportunities for corrective action to make the process more consistent and reliable. Quality improvement methodologies like Six Sigma and Lean Six Sigma are often used to systematically identify and eliminate assignable causes of variation to achieve higher levels of process performance and product quality. By distinguishing between chance causes and assignable causes, organizations can make data-driven decisions to enhance their processes and reduce defects or errors. Examples of chance causes or common cause variation. Natural environmental variability. Temperature fluctuations in a manufacturing facility due to changing weather conditions. Seasonal variations in product demand. Next is inherent material variability. Variations in the moisture content of wood used in furniture manufacturing. Variability in the size and weight of agricultural produce. Next is operator skill and behavior. Day-to-day fluctuations in the speed at which a skilled operator assembles components. Minor differences in the typing speed of data entry clerks. Next is inherent machine variability. Minor variations in the cutting speed of a machine tool. Random variations in the output of a printer. Examples of assignable causes or special cause variation may be due to machine malfunction. A machine breaking down, causing a significant disruption in production. A malfunction in an automated assembly line leading to defective products. May be due to human error. A worker making an incorrect setting on a machine. Data entry errors leading to incorrect customer billing. Due to supplier issues. Resealing subpar raw materials from a supplier, causing defects in the final product. A supplier changing the specifications of the materials without notification. Due to power outage. A sudden power outage disrupting computer servers and data processing. Loss of electricity causing a halt in production on an assembly line. Due to natural disasters. Flooding of a manufacturing facility due to heavy rains, leading to equipment damage. Earthquakes causing structural damage to a building, affecting production. Due to sabotage or tampering. Deliberate acts of vandalism or tampering with equipment or products. Employees intentionally introducing defects in products. If only common cause is present, you can predict the future outcome. To manage any process and reduce variation, the variation should be traced back to its sources. The first step is to make the distinction between common and special causes of variation. Common causes refer to the many sources of variation that consistently acting on the process. Common causes within a process variation. Common and special causes processes that have undergone several cycles of continual improvement produce a stable and repeatable distribution over time. This is called in a state of statistical control. In statistical control, or sometimes just in control. Common causes yield a stable system of chance causes. If only common causes of variation are present and do not change, the output of a process is predictable. If assignable cause is also present, you cannot predict the future outcome. Special causes, often called assignable causes, refer to any factors causing variation that affect only some of the process output. They are often intermittent and unpredictable. Special causes are signaled by one or more points beyond the control limits or non-random patterns of points within the control limits. Unless all the special causes of variation are identified and acted upon, they may continue to affect the process output in unpredictable ways. If special causes of variation are present, the process output will not be stable over time. The changes in the process distribution due to special causes can be either detrimental or beneficial. When detrimental, they need to be understood and removed. When beneficial, they should be understood and made a permanent part of the process. With some mature processes, the customer may give special allowance to run a process with a consistently occurring special cause. Such allowances will usually require that the process control plans can assure conformance to customer requirements, and protect the. Next is process control. If you analyze this, you will find this is a out-of-control process which is due to assignable cause of variation or special cause of variation. If you analyze this one, you will find this is under control process where only chance cause or common causes of variation present. There is an important connection between the two types of variation just discussed and the types of action necessary to reduce them. Simple statistical process control techniques can detect special causes of variation. Discovering a special cause of variation and taking the proper action is usually the responsibility of someone who is directly connected with the operation. Although management can sometimes be involved to correct the condition, the resolution of a special cause of variation usually requires local action, that is, by people directly connected with the operation. This is especially true during the early process improvement efforts. As one succeeds in taking the proper action on special causes, those that remain will often require management action, rather than local action. These same simple statistical techniques can also indicate the extent of common causes of variation, but the causes themselves need more detailed analysis to isolate. The correction of these common causes of variation is usually the responsibility of management. Sometimes people directly connected with the operation will be in a better position to identify them and pass them on to management for action. If you find this type of result, then it shows process is in control but not capable of meeting customer specification. This happens due to excessive common cause variation. Next, if you find this type of result, then it shows process is in control and capable of meeting customer specification. This happens due to excessive low common causes of variation. Overall, the resolution of common causes of variation usually requires action on the system. Only a relatively small proportion of excessive process variation, industrial experience suggests about 15%, is correctable locally by people directly connected with the operation. The majority, the other 85%, is correctable only by management action on the system. Confusion about the type of action to take is very costly to the organization in terms of wasted effort, delayed resolution of trouble, and aggravating problems. It may be wrong, for example, to take local action, such as adjusting a machine when management action on the system is required, such as selecting suppliers that provide consistent input materials. Nevertheless, close teamwork between management and those persons directly connected with the operation is a must for enhancing reduction of common causes of process variation. Next is, what is control charts? A control chart is a graphic representation of the variation in the computed statistics being produced by the process. Next is, what are the advantages of control chart? It shows the process variation with time. It indicates statistical control or lack of it. It enables pattern interpretation. It helps in detection of changes in the process. Next is, what are the steps to select control chart? First step is selection of critical to quality characteristics. Here, always select control items that are very critical for business process, such as characteristic that is creating highest no of non-conformities. Then determine a convenient point in the production process to locate the chart. This point should be early enough to prevent non-conformities and to guard against additional work on non-conforming items. Second step is selection of control chart. Here you have to check data type, which may be variable or attribute data. Then check sample size feasibility. Then check lot size, whether lot size is variable or constant. Important note, control chart creation is based on normal distribution and center limit theorem. Third step is sample size selection, means sample selection should be based on rational subgroup methodology. Variations within subgroup values should be minimum and variation between subgroups should be maximum. Widely accepted subgroup size N4, 5 and number of subgroups 20 for variable data, 50 for attribute data. Fourth step is data collections, means selection of measurement system. Don't round off value. Use specified check sheets. Note down all assignable causes occurred at process during data collection. For selection of right control chart you have to follow few steps. First note what is the sample size, what is range value, and what is the standard deviation value. After this you have to see the data type. Whether it is a variable data or discrete data. If it is variable data, then see what is the sample size. If the sample size n is equal to 1, then use x bar mr chat. If the sample size n is greater than 10, then use x bar s chat. Then if the data is discrete data, then see whether data is related to number defects in a pieces or number defective pieces. If the data is related to number of defects in a piece, then see whether the sample size is constant or variable. If the sample size or lot size is constant, then use C-chat. If the sample size is variable, then use U-chat. If the data is related to number of defective pieces, then see whether the sample size or lot size is constant or variable. If the sample size is constant, then use NP-chat. If the sample size is variable, then use P-chat. Next is key formulas used in SPC. Grand average mean calculation. Grand average mean or X double bar is equal to sum of sample mean to be divided by total number of sample group. But before this you have to calculate each sample group mean, which is X bar. Next formula is average range calculation. Average range or R is equal to sum of all ranges of sample groups to be divided by total number of sample groups. Next formula is upper control limit calculation. Upper control limit UCL X bar is equal to X double bar plus A to R bar. Next formula is lower control limit calculation. Lower control limit ALCL X bar is equal to X double bar minus A to R bar. Next formula is upper control limit calculation for range. Upper control limit UCL for range is equal to D4 R bar. Next formula is Let's see an example. A manufacturer produces body subframe support gusset. Several holes of various sizes must be punched into the gusset to accommodate pipe connections that must be made to the engine parts. If any one of these holes is punched in the wrong location, the gusset becomes a piece of scrap metal at considerable cost to the manufacturer. Experience with the hole punching process suggests that substantial changes, machine resets, equipment lubrication, and so forth. First see the sample data which is taken into 20 minutes time interval. Here subgroup size is 5. Means 5 sample taken in 20 minutes time interval. Total subgroup is 20. Then calculate subgroup mean. First calculate sum of each values in each subgroup. Then this total value to be divided by total number of sample in each subgroup, which is 5. Finally, you will get mean of each subgroup. Likewise, calculate mean value of each subgroup. Then calculate subgroup range. For this, find which is the maximum value in a subgroup. Then find which one is minimum. Then calculate range. Means maximum minus minimum value. Likewise, calculate range of each subgroup. Finally, you will find the mean and range of each subgroup. If we plot a graph using mean and range, which will look like this. If we plot a graph considering mean or x bar in y-axis, this will look like this. If we plot a graph considering range r in y-axis, this will look like this. Then calculate grand average mean or x double bar, which is sum of all subgroup mean value, and divide total number of subgroup. And the result will be 3.006. Then calculate average range. Formula for average range or R bar, which is equal to sum of each subgroup range value. Then divide same with total number of subgroup, which is 20. Then calculate upper control limit for x bar. UCL x bar is equal to x double bar plus a 2R bar. As sample size n is 5 for this example, so a 2 value will be 0.59. So UCL will be 3.055. Then calculate low control limit for x bar. Lower control limit or LCL x bar is equal to x double bar minus a 2R bar. So LCL will be 2.957. Then calculate upper control limit for R, so UCL for R will be capital D4R bar. As sample size n is 5 for this example, so D4 value will be 2.11. UCL for R will be 0.1797. Then calculate lower control limit for R, so LCL for R will be capital D3R bar. As sample size n is 5 for this example, so capital D3 value is 0. LCL will be 0. Next is plot control chart using x bar R. After making control chart, observe the control chart. Here you will find x bar chart is under control limit, but range chart is out of control. Because range of subgroup 7 and 17 out of upper control limit. This is due to assignable causes of variation. Then recalculate x double bar, range, upper control limit and lower control limit. Subgroup 7 and 17 not considered for calculation. So total subgroup capital N will be 18. Next, recalculate average range for x bar. Next, recalculate upper control limit and lower control limit for x bar. Next, recalculate upper control limit and lower control limit for range. Next is plot control chart using x bar R. After making control chart, observe the control chart. Here x bar chart not in control, because subgroup 1 and 13 are out of upper control limit. This is due to assignable causes. So drop subgroup 1 and subgroup 13, recalculate control limits again. Next, recalculate x double bar. Next, recalculate average range for x bar. Next, recalculate upper control limit and lower control limit for x bar. Next, recalculate upper control limit and lower control limit for range. Then report x bar R chart. Here both x bar and range chart are under control. Next is different coefficient used for control limit calculation. A2 used for 6 common rules for control chat pattern analysis. For this, divide tolerance zone in 3 equal zones, such as red zone, yellow zone, and green zone. This formula is used for zone width calculation. First rule for pattern analysis. Rule 1 is if one or more than one point is out of control limit, then you can conclude that special cause present in the process. So to eliminate this special cause, identify root cause and take action. Second rule. 2 points out of 3 consecutive points between warning limit means in red zone and corresponding control limit. This may be due to special cause. So to eliminate this special cause, identify root cause and take action. Third rule. 2 consecutive points between warning limit and corresponding control limit. This may be due to special cause. So to eliminate this special cause, identify root cause and take action. Fourth rule. 7 consecutive points on one side of the center line. This may be due to special cause. So to eliminate this special cause, identify root cause and take action. Fifth rule. 7 consecutive points having upward trend. This may be due to special cause. So to eliminate this special cause, identify root cause and take action. Sixth rule. 7 consecutive points having downward trend. This may be due to special cause. So to eliminate this special cause, identify root cause and take action. This is all about control chat. Hope you understand how to use control